Good morning, everybody. We are continuing our Chapter 8 discussion on bonding, and this is going to be our last lecture in Chapter 8. The rest of it we'll be doing together in class. So as we take a look that we are talking about the energy effects in binary ionic compounds. Keep in mind that ionic means a metal to a nonmetal to form that compound. Well, it's not just going to happen because it happens. We have to take a look at the amount of energy that's there. So that energy in an ionic compound is called lattice energy. So we can see that it's the change in energy that happens when a gaseous ions are packed to form an ionic solid. So what this is simply saying is how strong are these ions attracted to create something in a solid state. So we can see that if I have an ionic solid, you should continue to recognize, and I will keep saying this, that if I have an ionic solid, I have a metal to a nonmetal. I have a cation to an anion. This is represented here again. My cation with my positive charge losing one electron. This is a metal. To an anion with a -1 charge. This is a nonmetal. This is going to form my solid ionic substance. Well, in order for this to happen, I kind of covered up this negative charge right here. That is a release of energy. So we should understand that if I have a release of energy, I have an exothermic reaction. And Le just means lattice energy. So it's a release of exothermic energy whenever I am forming an ionic solid. Well, how much energy is needed? And that's what we're going to take a look at. So if I take a look at lithium fluoride, you can notice again ionic, metal, nonmetal, and I have this really small little lithium right here. In order for this to stay together, I have to maximize my ionic attraction between this positive and this negative, but I also have to minimize because I know I have these positive cations here that are going to repulse each other, and then I also have these negative anions that are not going to like each other either. So what it has to do is it has to have 6 of each of these around here to maximize this. So each lithium ion right here is surrounded by 6 fluoride ions, and conversely the same is true. Each fluoride ion is surrounded by 6 lithium ions. So if they are both a +1 and -1 charge, it's easy to pretty much figure out its lattice energy. So this diagram I realize is a little bit small. You might need to go ahead and take a look at this in your textbook. But as we take a look, we can see that we are increasing in energy. Now this comes from Coulomb's law, C-O-U-L-O-M-B-S, Coulomb's law. It talks about the amount of lattice energy that is there is a constant that Coulomb has come up with, K for constant, and it is the product of the charge of ion 1 with the charge of ion 2 divided by the radius, meaning the distance apart that the cations and anions have to be to maximize their attraction. And so this is shown here in a diagram that looks a lot easier to understand. So you can see that I have a great amount of lattice energy here. Well, take a look at this. I got magnesium that has a +2 charge. Remember that those 2 electrons are being transferred. And then I have sodium down here that has a +1 charge, so 1 electron is being transferred. Logically, it should make sense to you that it takes more energy to transfer 2 electrons versus 1 electron. And remember, they're doing that ionization energy is there so that they can have a noble gas configuration. And so how can we determine this lattice energy? Now this next slide is not in your notes, so you might need to add it somewhere or put it on a piece of paper, whatever you need to do. But how can I tell the amount of lattice energy that is needed? We're predicting this. Well, one way is by the charge. So we just talked about that the greater the charge, the greater the lattice energy that's going to be needed. So I can very easily say that if I take a look at sodium +1 bonding with chlorine, and I have sodium chloride versus sodium again, or let's see, if I do magnesium, let's do that. Let's just do it nice and easy so you can see this. So if I have magnesium +2 and I have bonding with sulfur -2, this one is going to require greater lattice energy, transferring up 2 electrons. It has a greater attraction, so it's going to take more energy there to create this bond. All right, well, let's take a look at if I have something like sodium again with a +1 charge, and I have oxygen, so I have sodium oxide, and then I have calcium with a +2 charge bonding with oxygen for my ionic bond. Well, which one's going to release more energy? Well, we also have to pay attention to our solubility rules. Sodium oxide is very soluble in water, all right? So if it's pretty soluble, that means it's going to break apart pretty easily, so it probably doesn't take as much energy to hold this bond together. If I take a look at my solubility rules for calcium oxide, the calcium oxide is less soluble, far less soluble, and so it's going to be a lot harder to break that bond. So that's another way is remembering our solubility rules. All right, and the second thing is the size of the ions. What happens if the charges are the same? So if I take a look again, we'll just do our sodium because that's an easy example. We have sodium with fluorine, so we have sodium fluoride, and then I have sodium again with chloride. So I have NaCl, that's what you have at home, or sodium fluoride. Well, they have the same charges, so I cannot apply that. Then I have to take a look at the size of the ions. Fluorine is a much smaller anion than chlorine is. And so because it's so much smaller, it should make sense to you that it's packed so much tighter. If it's packed a lot tighter, you're holding on to that, it's going to take greater lattice energy to break that apart. So the size of the ions are going to play a part. We've talked about in class, again, we'll review this, that as I go across the periodic chart, my atomic radii decreases, and as I go down the periodic chart, it increases. Apply those basic principles here, and you'll be able to understand lattice energy. Now, it's really difficult to make predictions of polyatomic ions, meaning like phosphate or nitrate, so we're just going to stay away from those. We're going to keep it nice and simple. So you just need to take a look at the charge or the size of the ions. Now, again, we are still talking about ions. We're still talking about ionic substances. So the last section that I want to talk about is partial ionic character of covalent bonds. All right, seems kind of like I'm talking about a bunch of different things, but ionic character, again, remember we are transferring our electrons, and then we have covalent bonds that we know are sharing their electrons. Well, can we still have dipole moments? And the answer is yes, but we're going to take a look at simply ionic substances. So here, you would have to be given the difference in electronegativity. So you'd have to be given those values. So I subtract the difference between these two, and I'm going to divide by the one that has the higher electronegativity times 100, and it gives you the percent ionic character. So if I take a look at sodium and chlorine, I look on my electronegativity sheet, and sodium has electronegativity difference or value of 0.9. Chlorine is 3.0. This should make sense to you because sodium wants to lose that electron. Chlorine does not. So my difference here is 2.1. So my percent is going to be 2.1 over the one that has a higher electronegativity, so that would be my chlorine, and put that into a percent, and that's going to give me 70%. So what this means, you guys, is that 70% of the time, the electron is going to be closer to the chlorine than it is to the sodium. Again, it wants to gain that electron, so that should make sense that that value is higher. Now, you could have done this without finding the percent ionic character. You guys understand that. It's just another term that they might throw at you. So if it's less than or equal to 10% character, it's going to be covalent. And so what that means is that the I'm spelling covalent wrong. The electrons are going to have a higher tendency of being shared instead of transferring. If it's greater than 50%, then they talk about that as being highly ionic in character. Obviously, it looks like there's a little bit of a gray area here, which of course there is. And those would take into account the polyatomic ions, the ones that have more than just a single cation with an anion. Okay, so we can do most of the questions now that I have assigned. There's a few here that I'll tell you in class that you won't be able to do yet until we cover the next sections. You can see that the next sections we're going to start taking a look at structure and shape, and we're going to talk about these in class just because it's going to be easier to pull out models and you guys can ask some more questions with that. All right, so hopefully you have all of your notes filled into here. Have an awesome day.